Welcome back, students. In the previous lecture, we talked about energy and heat. In today's lecture, we will talk about how heat can change either temperature or the state of matter. This is a typical weather forecast for beautiful, sunny Southern California, where, for example, Huntington Beach will enjoy 76 degrees weather, whereas here in Walnut we have 85 degrees, and in Palmdale it is 96 degrees. Now this pattern does not change much throughout the year. Why is that? Why is it at the beach it tends to be much cooler, and as you go inland it becomes much warmer? It turns out a contributing factor to this is an idea called heat capacity. Now you can think about heat capacity much like thinking of someone's anger capacity. If you are someone who has a high anger capacity, you can receive a lot of agitation before you change your mood to become angry. On the other hand, on another day, if you have low anger capacity, the smallest agitation can change your mood and even change your action. That simile can be applied to heat capacity. If something has high heat capacity, it can gain or lose a lot of heat without changing much of its temperature, whereas something that has low heat capacity will require very little amount of energy to change its temperature. That is why even though water and land both receive the same amount of heat from the sun, water can absorb much of that heat without changing much of its temperature, whereas land will increase its temperature drastically upon absorption of heat. And that is why if you live near the coast, near the water, you will experience cooler temperatures. And as it turns out, this quality to absorb heat and changing temperature is unique to every substance. And because of that, it is called specific heat. Specific heat is a physical property that is defined by the amount of heat that raises 1 gram of a substance by 1 degrees Celsius. Again, that just means how much heat it needs to raise a substance by 1 degree Celsius. If you have a gram of something that has high heat capacity, it will require a lot more energy to raise it by 1 degree Celsius than if you have another gram of something that has low heat capacity. The mathematical equation for specific heat then is equal to heat divided by the product of mass times the change in temperature. The change in temperature is denoted here as delta T. The triangle represents delta, which means change in. What is the unit of specific heat? Since heat has units of calories or joules, mass has units of grams, and temperature has unit of Celsius, the unit for specific heat is calories per gram Celsius or joules per gram degrees Celsius. As I mentioned before, every substance has its unique specific heat. This is a table of some of those substances. If you notice, the elements on the top are all metals, and it turns out metals do have very low specific heat. You may have first-hand experience of this. For example, in the summer when you have left your car under the sun for quite some time, the inside of your car may heat up. And when you try to enter your car, sit down, pull the buckle over yourself, you may be mildly burnt by the buckle, but not by your seat. Why is that? Because the buckle is made of the metal, which has a low heat capacity, while your seat is a non-metal, which tends to have a higher heat capacity. Again, the low heat capacity means that your metal, receiving the same amount of heat from the sun, heats up much more because of its low specific heat relative to that of the non-metal seat. Another testament to the low specific heat of metals is their utility. So when you are cooking, you want heat to transfer directly to your food as much as possible. So you want to use something that can absorb and release heat readily. So often your pots and pans are made of metals. To flesh out the idea of specific heat, let's focus again on two substances, water and aluminum. Aluminum here represents a lot of the elements that is found in the land analogy that we talked about in the previous slide. The specific heat of aluminum is 0.214 calories per gram Celsius, whereas water is 1.00 calories per gram degrees Celsius. So the specific heat of water is 5 times that of aluminum. Another analogy to illustrate this point is to think of specific heat as price tags. you can say that water costs $1 per gram Celsius, while aluminum costs only $0.21 or 21 cents per gram degree Celsius. So if you have $1, you can raise your water by 1 degree Celsius. But if you have the same amount of money, that $1, you can raise your aluminum by 5 degrees Celsius. In the same sense here, if you give 1 gram of water 1 calorie, it will increase 1 degree Celsius. But if you give 1 gram aluminum 1 calorie, it will increase by 5 degrees Celsius. Hopefully that analogy helps you understand a little bit more about specific heat. Remember that the unit of energy is calories or joules, so the specific heat also has 2 units, whether you state it in calories per gram Celsius or joules per gram Celsius. Depending on whether you want to calculate calories or joules, you may have to decide which specific heat value you have to use. Let us now calculate the heat involved when you raise or lower a temperature of a substance. Going back to our original equation, where specific heat is equal to heat divided by grams times temperature, if I want to rearrange this equation to get only heat, I must multiply both sides by grams and change in temperature. And so I have heat is equal to specific heat times change in temperature times grams. Now to write this equation a little bit more neatly, I can rearrange a few things. So the heat equation is heat is equal to mass times specific heat times temperature change. Boiling that down to a more simple equation, I get Q is equal to 𝑚⁴, where again Q is the symbol for heat, M is a symbol for mass, SH is a symbol for specific heat, and delta T is a symbol for temperature change. In other chemistry courses, you may see specific heat abbreviated as a C instead. So I will use these two equations interchangeably. They mean the same thing. Q is either equal to 𝑚⁴ or Q is equal to 𝑚cat, where C is specific heat. What about the units? Mass has a unit of gram, specific heat has a unit of calories or joules per gram degrees Celsius, and change in temperature has the units of degrees Celsius. From this unit analysis, I can see that grams will cancel each other out and degrees Celsius will cancel each other out, leaving calories as the only unit left, which is exactly what I want because heat is measured in calories. Now you want to use this equation whenever you see that heat causes a change in temperature. Let's take a look at an example. The problem states how much heat in calories is released by 24.8 grams of iron if its temperature decreased from 24.5 degrees Celsius to 20.2 degrees Celsius. In such a problem like this, in my analysis, I asked myself what is needed, and it turns out the needed is heat. And what is this heat doing? This heat, it turns out, is changing temperature. As soon as I see that this heat changes temperature of a substance, I automatically think of 𝑚cat. Q is equal to 𝑚cat. Again, Q is heat, so in order to solve for heat, I must know M, C, and delta T. M is 24.8 grams. The specific heat of iron is not given in this equation, so I would have to look it up in a table somewhere. The specific heat of iron turns out to be 0.108 calories per gram degrees Celsius. Notice that I use 0.108 calories per gram degrees Celsius and not 0.452 joules per gram degrees Celsius because calories is a unit of heat that I want at the end. What about delta T? Remember that delta T is a change in temperature. To calculate the change of something, you take the final state minus the initial state. In this case, it's 20.2 degrees Celsius minus 24.5 degrees Celsius, which is negative 4.3 degrees Celsius. Now that we have all of our variables, let's plug it into our equation. Q is equal to 24.8 grams times 0.108 calories per gram degrees Celsius times negative 4.3 degrees Celsius. I like to first cancel out my units. I can see that grams will cancel out and degrees Celsius will cancel out, leaving me with only calories, which is what I need. Going into my calculator, I plug in these numbers and it gives me this number. Looking at my significant figures, 24.8 has 3 sig figs, specific heat has 3 sig figs, but my delta T only has 2 sig figs, so my answer should have 2 sig figs, rounding that up to negative 12 calories. Notice that the Q is equal to a negative number, because remember, when heat is being released, we annotate that with a negative number. When heat is being absorbed, we annotate that as being a positive number. So what if in a similar question, the temperature, instead of decreasing, is increasing from 20.2 degrees Celsius to 24.5 degrees Celsius? Can you give me an answer even without doing it in a calculation? In fact, you can, because the only thing that changes in this problem is that T final and T initial are flipped. Instead of 20.2 minus 24.5, it's 24.5 minus 20.2, giving you a positive 4.3. So when you plug it into this equation as you see here, the only thing that changes is this positive sign, giving your answer to be a positive sign, which again makes sense. If Q is a positive number, it is being absorbed. The only reason a temperature can increase is that heat is being absorbed. Let's do a checkpoint. The question reads, a layer of copper on a pan has a mass of 135 grams. How much heat in kilojoules will raise the temperature of the copper from 26 degrees to 328 degrees Celsius? Again, pause this video to solve this problem. Hopefully you found an answer in the options below. To solve this problem, again, I would ask myself, what kind of heat is being involved? It turns out that a substance is changing temperature, so I automatically go to my Q is equal to MCAT equation. Plugging in all my variables, my mass, my specific heat, and my change in temperature, checking that my units do cancel out, I will get a number from the calculator. Checking for sig figs, it seems there are 3 significant figures here, so my answer rounds up to 15,700 joules. It asks us to calculate in kilojoules, so I simply convert joules into kilojoules, which becomes 15.7 kilojoule. The answer is D. Alright, let's go to the second part of today's lecture, state changes. This is the section where we see that heat can sometimes change phase instead of changing temperature. Before we talk about that, let's review about the states of matter. We have 3 states of matter depicted here with water. In the solid phase, we have ice, where the molecules of solid water are very compact and not moving much. We also have water, where there is a little bit more movement, a little bit more space. And lastly, in the gas phase, we have water vapor, where the molecules are moving fast and farther away from each other. Remember that we said these movements are correlated with the amount of energy. The molecules in the solid have low energy, whereas molecules in the liquid has medium amount of energy, and molecules in the gas phase has a high amount of energy. So it turns out that when you are adding energy in the form of heat to, for example, a solid ice, the molecules start to move around much more until they become liquid. And at that point, we call it melting. Now the opposite can occur. You can remove energy from a liquid so that it stop moving so much that it becomes solid. We call that freezing. This can also happen between the gas phase and the liquid phase. Again, if we add energy to molecules of liquid water, it will start to move faster and faster and eventually lose the attraction for each other and break away from the liquid phase altogether into the gas phase. And we call that vaporization. The opposite process occurs where energy is lost and the water vapor molecules condenses back into the liquid phase. What I just discussed in these 2 examples is something called change of state or phase changes. And this is a process where matter changes from one state into another state. To reiterate and distinguish ourselves from the previous section, in this section, when heat is added or removed from a substance, it does not change the temperature of that substance, but rather it will change the state of that substance. Let's take a closer look at these phase changes. Let's start with the melting and the freezing point. The melting occurs when heat is added to a substance and it changes from a solid into a liquid, and this occurs at a temperature called the melting point. Whereas freezing is a process where heat is being removed from a substance and it changes from a liquid to a solid. This occurs at a temperature called the freezing point. It turns out the melting point is the freezing point. A solid can become a liquid, and a liquid can become a solid only at one point, and this point varies for different substances. What is a melting or a freezing point of a substance that you know? Hopefully you said water. Yes, water has a freezing point of 0 degrees Celsius, or we can say ice has a melting point of 0 degrees Celsius. So remember we said that in this process, heat is added or removed to change phase. Well, can we calculate the amount of heat? We can calculate that amount of heat using something called the heat of fusion. The heat of fusion is a value of heat added or removed to melt or freeze 1 gram of substance. So we can use this equation to solve for how much heat is being involved in melting or freezing. Q is equal to mass times the heat of fusion. This equation is very similar to our 𝑚₌ equation, the equation to solve for heat in changing temperature. Mass is still the same. Specific heat, remember, was a unique value to a substance, and so is 𝐻𝐹. The only difference here is that we do not have a delta T at the end because in our case, there is no change in temperature when there is a phase change. Just like the value of specific heat, the value of heat of fusion is a unique value for every substance. For example, the heat of fusion for water is 80 calories per gram. That means that for every gram of water, you need 80 calories to freeze or melt it. Let's do an example using heat of fusion. The question states, how many kilojoules are needed to melt 32.0 grams of ice at 0 degrees Celsius? Again, to analyze a heat equation, I ask myself, what is this heat doing? Is it changing temperature or changing phase? And I notice that it's changing phase, so I'm not going to use MCAT, but I'm going to use Q is equal to M times HF. Plugging in my variables, mass is 32.0 grams. Heat of fusion, because it is melting, is 334 joules per gram. Punching this into the calculator, I get 10,688 joules. I see that I only have 3 significant figures in my number, so I should round this to 10,700. Lastly, converting joules into kilojoules, I get 10.7 kilojoules as my final answer. And so again, this is a positive number because heat is being absorbed. Let us now talk about the second point. The second point relates the phase change between a liquid and a gas, which is evaporation and condensation. Evaporation is a process where when heat is added to a substance, it changes it from a liquid to a gas. This happens at a temperature called its boiling point. The opposite scenario is condensation, where heat is removed from a substance to cause it to change from a gas to a liquid. Again, this also happens at the same temperature. For water, the boiling point is 100 degrees Celsius. Similar to heat of fusion, you can also calculate the heat that is involved in evaporating or condensing a substance. It's called heat of vaporization or condensation. Again, this is a value of heat required to vaporize or condense 1 gram of a substance. The equation is very similar to the heat of fusion. It is basically the same equation except replacing heat of fusion for heat of vaporization, HV. For water, the heat of vaporization is 540 calories per gram. Again, that means you need 540 calories to vaporize 1 gram of water or to condense 1 gram of water vapor. Let's do a quick example here. Calculate the calories of heat released to condense 35 grams of water. Again, I say heat is used to change phase, so I'm going to use M times HV. We see condense, so we need HV, not HF. The mass is 35 grams multiplied by 540 calories per gram, which turns out to be 18,900. Taking a look at sig figs, we see that we have 2 sig figs, so our final answer should also have 2 sig figs. And also a note on positive and negative signs, we see that the heat is being released, so we should see Q as a negative number. So our final answer is Q is equal to negative 19,000 calories. Checkpoint. How many kilojoules are released when 25 grams of water at 0 degrees Celsius freezes? Pause this video to solve this problem. Okay, so we see heat is used to change phase, and particularly into freezing. So we say Q is equal to mass times heat of fusion. Plugging in the value for mass and the heat of fusion of water, and plugging it into the calculator, we get 8,350 joules. It asks for kilojoules, so we convert that to 8.35 kilojoules. We put the negative sign in front of that to signify that is it being released. We see the answer there is C, even though it doesn't have a negative sign. Maybe the writer argues that you are saying 8.35 kilojoules is released, which is the same as saying negative 8.35 kilojoules. Now, to end our discussion in this chapter, we will add up our knowledge of when heat changes temperature and when heat changes phase into problems where you may have to calculate one or the other or both heats. And in these complicated equations, you may use a heating curve. A heating curve is a visual to let us know how is temperature being affected as you are adding heat. Because remember, in one case, adding heat can cause temperature to increase or to change phase. Temperature is graphed on the y-axis and heat is graphed on the x-axis. How to read this curve is to go from left to right as heat is being added to ask yourself, how is the temperature being changed as heat is being added? So for example, in this heat curve, you start out at negative 40 degrees of solid water or ice, right? If you follow along this red path, it's moving from left to right, but also bottom up. As you are adding heat into the solid at negative 40 degrees, it goes past negative 20, then it creeps up all the way to 0 degrees. Once you get to 0 degrees Celsius, the more heat you add to it, it doesn't continue to rise in temperature. Instead, at this point, called its melting point, the more heat you add to it is used to change its phase. Once all of the ice has melted into liquid, when you add more heat to it, at that point is when you start to change temperature again. So in this part of the curve, it is water increasing in temperature as heat is being added. With water increasing in temperature, there is a limit to it, and it hits the limit at 100 degrees Celsius. For water, 100 degrees Celsius is the boiling point. So as you are adding heat to the substance, it does not change temperature, rather it is changing phase. Until you have transformed all of the liquid into gas, adding more heat will not change temperature. Once you have transformed all of the liquid water into its gas phase, adding more heat then will change temperature yet again, now changing the temperature of the gas. Okay, so looking at a curve like this, you see two types of lines. First line is a diagonal line. And what do you notice about these diagonal lines? These diagonal lines correspond to change in temperature. So the heat involved in these diagonal lines is mcat. The other type of line is the horizontal line, or the plateau. It involves no change in temperature, but change in phase. So to calculate these heats, you will use mass times heat of fusion or mass times heat of vaporization. Again, I want to emphasize that in order to solve more complicated heat problems, you want to draw these heating curves to break down the individual steps to let you know how many heats, how many Qs you are solving. The difference between a heating curve and a cooling curve, as you may have guessed, a cooling curve will start at high temperatures and start to decrease downward, whereas a heating curve starts at low temperatures and increases. Another aspect of these heating curves that is important is that the horizontal, the plateaus, the temperature at which it occurs varies for every substance. In this case, for water, it is 0 and 100. For other cases, let's say for a metal, the plateau for melting is all the way in the thousands of degrees Celsius. You may have to draw your heating curves accordingly. Okay, let's do an example of a combined heat calculation. So the problem states, calculate the total heat needed to convert 15.0 grams of liquid ethanol starting at 25 degrees Celsius until it vaporizes into a gas at its boiling point of 78 degrees Celsius. Some other information you may need is that ethanol has a specific heat of 2.46 joules per gram degrees Celsius and a heat of vaporization of 841 joules per gram. So the first thing you want to do is draw a heating curve to simplify what is going on. You ask yourself, is heat going to change the temperature? Is it going to change phase of the substance? Or is it going to do both? From that, you can figure out how many Qs you have to calculate. After adding up all the Qs, you will know the final total heat. So let's start with drawing the heat curve. And on this heat curve, on the x-axis, you want to have heat added or heat removed. And on the y-axis, you want temperature. It states here that the liquid starts at 25 degrees Celsius, and you need to increase its temperature to 78 degrees Celsius, right? To increase the temperature of something in the same phase, you want to draw a diagonal line connecting 25 degrees as you add heat to 78 degrees Celsius. And so you would call that Q1. But you are not done, since adding heat in this process only changes its temperature. You have not transformed the liquid into the gas yet. So you need to keep on adding heat to change its phase. Adding heat to change the state of a substance is a horizontal line, which corresponds to another Q, Q2. Once we have defined all of our Qs, we just have to solve for them. Again, Q1 involves changing in temperature, so I would use MCAT. The mass of ethanol is 15.0 grams. The specific heat of ethanol is 2.46 joules per gram degrees Celsius. And then it changed from 25 degrees to 78 degrees. Solving for this, I get 1,955.7 joules. Now I have underlined the tens place here to signify, to keep track of my significant figures. I see that this value has 3 sig figs, this 3 sig figs, this will also have 3 sig figs after you do the subtraction, so my answer should be to 3 significant figures. But I do not want to get rounded just quite yet. I only want to do rounding at the end. Whereas for Q2, I am changing phase, and the phase change here is from liquid to gas, so I need heat of vaporization. And conveniently, that is already provided for me as 841 joules per gram. I multiply that by the mass of 15.0 grams to get 12,615 joules. From here, there are 3 significant figures, so I underline that 6 because 1, 2, and 6 are significant, 1 and 5 is not. Again, I do not want to round just yet. For the final answer, to get the total heat, I just add Q1 and Q2 to get 14,571. Remember that this is an addition problem, so I must apply addition significant figure rules. Since this is in the tens place and this is in the hundreds place, my answer is only significant to the hundreds place. So I must drop the 7 and the 1, and that rounds up to 14,600 joules. Alright, to round up our discussion, we will talk now about sublimation and deposition. Previously, we have talked about the phase changes that occurs between a solid and a liquid, calling that melting and freezing. We have also talked about this phase change between a gas and a liquid, calling that vaporization and condensation. It turns out there is also a phase change that we're missing here between a solid and a gas, and that's called sublimation and deposition. We will not do any math calculation with respect to sublimation and deposition. All you need to know is that it exists and what it is. Again, when something sublimes, the molecules in the solid transitions directly into the molecule of a gas, skipping the liquid phase. The same thing for deposition. The molecule in a gas phase freezes directly onto a surface becoming a solid without ever going through the liquid phase. Some examples you may recognize from this is, for example, dry ice. Dry ice, which is solid carbon dioxide. You can buy dry ice at the supermarket. It stays cold for a very long time, so it might be good on your picnics. But anyways, as you can see from this picture, dry ice is solid, but it has this vapor around it, and that's gaseous carbon dioxide. So you can say that carbon dioxide solid sublimes into carbon dioxide gas, creating this kind of fog. It's actually used in Hollywood or film sets to make fake fog or gas. Another example that you might see on a more regular basis is freezer burn. What happens in freezer burn, there are water vapor molecules, and it gets so cold that the water vapor molecules deposits directly onto your food from gas phase into solid phase. Alright, so that was a lot of calculation for this lecture. But hopefully by the end of this lecture, you should have a good understanding of specific heat and to use it to calculate the heat that is lost or the heat that is gained when you have temperature changes. You should also be able to calculate specific heat if all the other variables are provided for you. Secondly, you should be able to describe the changes between the states of matter and to calculate the energy that is associated with it.